Welcome back to this fifth video dedicated to the FCC reaction section. In the first four parts, we have described the different sections of the reaction zone, the characteristics of the feed, the injection of the feed into the reactor, and the chemical reactions involved in the reactor. It's now time to focus on the selectivity of the process. The selectivity of a catalyst is simply quantifying the molecules that form during chemical reactions. Or, in other words, it answers the following question. How much gas, gasoline, diesel are we going to produce in the FCC reactor? First, some of the VGO sulfur is converted into H2S. You can see in the table that about 50% of the VGO sulfur is transformed into H2S. Then we see that we produce a small amount of hydrogen, about 0.2% by weight of the fresh feed. Then methane is produced, and a little ethane and ethylene, about 3% by weight of the fresh feed. This mixture of H2S plus C1 plus C2 will be routed to the refinery fuel gas network and ultimately burnt in refinery furnaces. Then we can focus on the products with a high added value. Propane but also propylene are produced. Propylene yield is tried to be maximized because propylene is a very popular cut for the production of polymers. The C3 cut represents approximately 4% by weight of the feed rate. Then we can have a look at the C4 cut. This cut is composed of N-butane, isobutane, and butenes. It represents about 9% by weight of the fresh feed. C4 are also very interesting molecules because we can use them to chemically form C8 and ultimately gasoline with a very high octane number in an alkylation unit, for example. Then light gasoline is found in a typical distillation range of 30 to 160 degrees C for about 35% by weight. Then heavy gasoline for about 14% by weight. These cuts are very good material to produce gasoline fuel. At this stage, we can clearly see that the gasoline represents about 50% by weight of the fresh feed. So, the FCC is a machine to produce gasoline. Then comes the LCO for light cycle oil, which is typically incorporable in the diesel pool for a value of between 15 to 20% by weight of the fresh feed. Then the HCO or heavy cycle oil, most commonly known as slurry, for a value of between 13 to 20% by weight. This cut is normally used as internal fuel for the refinery, but it can be a good material to produce fuel. Finally, the coke yield is about 5% by weight and has a fairly low variability regarding the feed quality. This coke is deposited on the surface of the catalyst and is therefore not recoverable in the form of final product. We will see in the following video what to do with it. It is now time to define the concept of conversion. It is defined as the percentage of the feed that is cracked into gas, LPG, gasoline, but also coke. In our case, we see that the conversion is about 70% by weight. Here is a graph that summarizes the typical yield in a FCC. We clearly see the very high amount of gasoline. Once we have this mixture of light molecules and coked catalyst, what to do with it? Well, we will see that in the next part in the videos dedicated to the FCC reaction section. In the meantime, do not hesitate to test your knowledge and subscribe to my YouTube channel. See you very soon for the sixth part. Bye bye!